Hello everyone, this is the second lecture of consolidation. So in this lecture I am going to discuss the Tajagi theory of consolidation. So in the first lecture I have discussed the introduction about the consolidation. I have also discussed the fundamental of consolidation. So let's start with the Tajagi theory of consolidation. So in 1925 Tajagi gave the theory for the determination of the rate of consolidation of a saturated soil mass subjected to the static and steady load. So basically the rate of settlement is related to the change in the effective stress, and the change in the effective stress is related to the change in the pore water pressure. So we can say the rate of settlement is directly related to the rate of dissipation of excess pore water pressure. And by using this theory we can predict the pore water pressure at any location at any time. So by deriving some basic relation, we had to take some assumption, and this assumption are: the first one is the soil is homogeneous and isotropic. The soil is fully saturated. It means degree of saturation is 100%, and there is no air is present. Means the degree of saturation 100%. We can write also S is equal to 1. And there is a two-phase diagram. There is a water and only solid particles are present. The solid particles and the water in the voids are incompressible. It means the compression in soil due to the compression in solid particles and the water in the voids are zero, and the compression in soil occur only due to the expulsion of water. That is called consolidation. So here the consolidation means primary consolidation. Don't confuse with that. The K, the coefficient of permeability of soil, has the same value at all points, and it remains constant during the entire period of consolidation. Dorsal is valid through the consolidation process. It means velocity, we can write velocity is equal to Ki, where K is the coefficient of permeability and I is the hydraulic gradient. Soil is laterally confined, and the consolidation takes place only in the axial direction. The drainage of water also occur only in the vertical direction. It means this is an example of first dimension consolidation. Means water is escaping out only in the vertical direction, only in one direction, but in the coming figure I mentioned the flowing of water occurring only in the vertical direction. The time lag in consolidation is due to entirely the low permeability of soil. The coefficient of compressibility and the coefficient of volume changes are constant. It means there is a unique relationship between the void ratio and the effective stress, and this relationship remains constant during the load increment. So the coefficient of compressibility and the coefficient of volume change are constants. So in the figure 7, the A part, so let us consider a saturated clay layer of a thickness 2H or 2D confined by two layers of sand, one of its top and one at its bottom. And when a uniform pressure of delta sigma is applied on the surface of the top layer of sand, the total stress developed in all the points in the clay layer is increased by delta sigma. So I explained in the previous lecture, in the first lecture of the consolidation. So whatever the total stress we apply in the soil layers, it will be registered by the pore water pressure and effective stress. Means the summation of effective stress and the pore water pressure will be constant at any time. Right? So then initially when the delta sigma or total stress is applied on the sand layer, so the pore water pressure will be constant throughout the thickness of the clay layer, and that is equal to the delta sigma. Means at this point of time means T is equal to 0, and we can say just after the application of the load, effective stress will be 0. So that is shown by a line that is called AB. So the AB line is showing the total water pressure that is called delta sigma throughout the thickness of clay layer, that is constant. So in the figure AB shown, and at a very long time, or we can say at T is equal to infinity, so the pore water pressure throughout the thickness of clay layer is 0. So that is shown by a line DC. So then at the line of DC, pore water pressure throughout the thickness of the clay layer is 0. So what is happening in between? So when the excess pore water pressure are developed, so due to the excess pore water pressure, water start escaping towards the upper and the lower sand layers. So the hydrostatic pressure drops to 0 at the top and the bottom of the clay layer. Because water has to travel very short distance to reach the drainage phase. So the dissipation of water at the top layer and the bottom layer is maximum, and this is reduced to 0 immediately after the application of load. But in between the top and bottom layer in the clay, the dissipation of pore water pressure is less as compared to top and bottom, because that water has to travel a maximum distance compared to top and bottom layer. So the dissipation of pore water pressure is less compared to the top and bottom. So the curve indicating the distribution of excess hydrostatic pressure is known as isochrone. Or we can say, in other words, if we will insert a number of piezometer at the different thickness, at a different height of the clay and at the various point of clay, so the water level will show in the every piezometer. So the line joining of water level in the piezometer, that will give the curve of isochrone, and that curve will call isochrone. So in the right corner figure, a number of isochrone are shown. So the at t is equal to 0, isochrone is vertical, straight line, that is vertical, because that at t is equal to 0, pore water pressure throughout the thickness of the clay layer is equal to constant, and it is equal to the delta sigma. So that is shown by the vertical line. But after the time t is elapsed, so at a t1, you can see the pore water pressure at the top and the bottom is 0. But in between the middle layer of clay, pore water pressure is not 0, because dissipation of pore water pressure compared to top and bottom is less. So a number of isochrone is shown, at a T2, at a T3, at T4, and again at a T is equal to infinity, and after a very long time, again isochrone is shown in vertical. So now we can proceed for derivation. So let us consider a soil element of a size dx, dz and dy. dy is the thickness of a soil element perpendicular to this figure. So we have taken a soil element, so derive our equation. So for this soil element, we can write this equation, and the left side of this equation is the amount of water entering minus the amount of water leaving per unit time, and the right side of this equation is the rate of depletion of water in the soil element per unit time. So both things we can equate, and we can get this equation. But this equation has written for 3-dimensional flow, but in this case flow is occurring only in the vertical direction, only in the z direction. So it means the velocity in the x direction and y direction are 0. So by giving the value of Vx and Vy 0, we can get this equation for 1-dimensional flow. So from the Darcy law, we can write V is equal to Ki. So we can write this, where dou H by dou Z is the hydraulic gradient, where dou H is the head loss and dou Z is the length of soil element in the direction of flow. Again, differentiation of Vz with respect to Z, we can get this value, and this H is the head which causes the flow and produces the excess pore water pressure. Here is the H is the region of the excess pore water pressure. So we can write head in terms of pore water pressure. So we can write H is equal to U by gamma W, where U is the pore water pressure. So by putting the value of H in the terms of pore water pressure, we can get this equation. So by putting the value of Vz, dou Vz by dou Z in the second equation, we can get this equation. So the second equation we can write like this. The volume of soil decreased by an amount equal to the volume of water which flow out. It means change in volume occur due to the expulsion of water. Means whatever the volume of water will escape, the same volume of soil will decrease. Same amount of volume of soil will decrease. Because the volume is decreasing only because of the expulsion of water. So we can write dou W by dou T, dou dx dy dz by dou T. So where the dx dy dz is the volume of soil element. Or we can write volume of void is equal to E into volume of solid, because the void ratio is the ratio of volume of void to the volume of solid. So volume of solid we can write in terms of total volume of soil. So we can write V is equal to V divided by 1 plus E naught, where V is the total volume of soil. So volume of voids we can write E by 1 plus E naught into dx dy dz, because V is the volume of soil and dx dy dz is the volume of soil element. So for a soil element we can write volume of void is equal to E by 1 plus E naught dx dy dz. Or we can write dw by dou W by dou T. So by putting the volume of void. So see, these three things are related. How it is related? So whatever the volume of change will occur in the soil due to the expulsion of water, means that whatever the volume of water will escape from the soil, the same amount of volume of soil will decrease and same amount of volume of voids will decrease. So means the rate of change of volume of soil is equal to the rate of change in the volume of voids is equal to the rate of water which is expulsion, which is going out, which is flowing out, right? So we can write, so by equating all this equation we can get this equation. So in the consolidation process, the excess pore water pressure dissipates and the effective stress increases, obviously, because the total stress whatever we have applied, that is in this case we have applied delta sigma. So whatever the delta sigma applied, it will be constant and is equal to the effective stress plus pore water pressure. So if pore water pressure will decrease, then effective stress will increase. So the total amount of total stress will be constant. So we seen that at any time that we can see that pore water pressure is continuously decreasing and effective stress is continuously increasing. So we can write change in effective stress equal to the change in pore water pressure, and we have taken the minus because the pore water pressure is decreasing. And we can write change in the void ratio equal to AB into the change in the pore water pressure. So AB is the coefficient of compressibility and AB is equal to change in the void ratio divided by change in the effective stress. So by using this equation we can write small change in the void ratio is equal to the AB into change in the pore water pressure. So by putting the value of change in the void ratio in terms of change in the pore water pressure, we can get this equation. Or by equating the above equation from the last equation, the rate of depletion of water we got in terms of pore water pressure. Or now in this case the above equation also we got in the terms of pore water pressure. So both things we can equate. So what we get after simplifying, because dx dy dz will cancel out, and after simplifying we can get this equation, where kz is the coefficient of permeability in the vertical direction, in Z direction. E naught is the initial void ratio. AV is the coefficient of compressibility. Gamma W is the unit weight of water. So more or less we can see that all this value are constant, or by summation or multiplication or division of constant value, it will get again a constant value, right? So we can say, we can write this equation where CB is the coefficient of consolidation, and this equation is called Terzaghi one-dimensional consolidation equation. So Terzaghi one-dimensional consolidation equation. So if you will see, so in this equation there is a pore water pressure, there is a time, there is a Z, right? So three things will give the result. After applying the all boundary condition, we can get the after applying the set of boundary condition, we can get the relationship between the pore water pressure, between the location, between the time elapsed. Okay. So we can get all these things. So here CB is the coefficient of consolidation, and it has a unit meter square per second, or we can write also meter square per day. So CB we can write also we can write K divided by MB by gamma W, where MB is another constant, that is called the coefficient of volume of compressibility, and we can write MB equal to AV divided by 1 plus E naught. So we can write K, that is coefficient of permeability. We can add CB into MB and into gamma W. So this whole formula, just remember, formulas are very important. And in the numericals problem, we will use all this formula directly. So just remember all this formula. So by applying a set of boundary condition in the Terzaghi one-dimensional consolidation equation, we can get the relation between the excess pore water pressure with respect to time elapsed T and location Z. So these boundary conditions are: at T is equal to 0, the pore water pressure is equal to the initial pore water pressure. At the initial pore water pressure is equal to whatever the total stress we have applied. And at T is equal to infinity, pore water pressure is 0 throughout the thickness of the clay. And T greater than 0, for the T greater than 0, the pore water pressure for the top and bottom layer of clay is 0. So this boundary condition we can apply to get the relation. So in the Terzaghi solution, three non-dimensional factors are provided, and these factors are very important. The first one is the drainage path ratio, and that is Z is equal to small z divided by H, where is the small z is the distance from the top layer of clay, and H is the maximum drainage path. Second is the time factor TV, that is equal to the CB divided by H square. See, in this formula, CB, because this was the came from the double drainage system, means water can be flow out from the top layer of sand and water can be flow out from the bottom layer of sand. So that was the example of double drainage system. So you can remember this formula, TV is equal to CB T divided by D square. So for the single drainage system, D will be equal to the thickness of clay, that will be in the case of 2H. And for the double drainage, D will be equal to the H. So whatever the drainage path, the distance of drainage path, that we will call a D. So you have to remember. So what is the case for the single drainage case, or for the double drainage case? You have to apply the H square, means D square. So it will be D can be a D H, D can be H by 2. So we just be focused, don't be confused in that. Okay. Third one is the degree of consolidation, or we can say consolidation ratio. So in terms of percentage, we can calculate the degree of consolidation. So in terms of pore water pressure, Ui minus U divided by Ui, where Ui is the initial pore water pressure and U is the pore water pressure at certain time. Degree of consolidation we can calculate by knowing the void ratio, E naught minus E divided by E naught minus EF, where the E naught is the initial void ratio, EF is the final void ratio, and E is the void ratio at certain time. And degree of consolidation can be calculated in terms of settlement. So where is the small delta small h divided by delta capital H into 100, where the delta capital is the total settlement and delta small delta h is the settlement for a certain time. And this relation we can get from this figure, where UZ is shown degree of consolidation in terms of fraction. So from this figure we can say at t is equal to 0, so we will put the value of t, we can get the TB is 0, time factor will be 0, and UZ is 0 means degree of consolidation is 0 in terms of fraction, so UZ is 0. At t is equal to infinity, so TB will be infinity because the TB is the proportional to the time t. So the degree of consolidation is 100%. In terms of fraction we can write 1. Or TB in between the 0 and infinity, so UZ will be greater than 0, less than 1 means the degree of consolidation will be greater than 0% and less than 100%. So for degree of consolidation for the less than or equal to 60%, we can use this formula to calculate the time factor, and that is TB is equal to pi by 4 into U square, where U is the degree of consolidation in terms of fraction, not in terms of percentage. Don't be confused. So for degree of consolidation for 60%, we can get TB value is 0.2826. So means after putting the U is equal to 0.6, we can get this value. So you can calculate also. And for degree of consolidation for greater than 60%, we can use this formula. So where U means the degree of consolidation is in percentage, not in fraction. In the first equation, in the tau v pi by 4 U square, the degree of consolidation was in the fraction, but here in the degree of consolidation in terms of percentage, right? So now we will solve some numerical problems. So clear our concept. So a 20-meter thick layer of sandwiched between a silty and sand layer and a gravelly sand layer. The layer experienced a 30 mm settlement in 2 years. So this is the figure. So the clay is confined between the two layers. The top layer is the silty sand and bottom layer is the gravelly sand. Okay. If the coefficient of consolidation of the layer is 0.003 centimeter square per second, the deposit will experience a total of 50 mm settlement in the next, how much year? We have to calculate the time for 50 mm settlement. So just note down what are the data given. So that is height of the clay layer is given 20 meter, T is given 2 years. So small settlement is given, small delta H is given 30 mm. CV value, degree of coefficient of consolidation is given 0.03 centimeter square per second. And here the case of the double drainage case. Okay. So first we will calculate the time factor. So we have the CV value, we have the time, and we have the H. So what H you will put? So see, H is the total. Here the total height of clay is 20 meter, but here the this is the system of double drainage system. Okay, so you have to take the H is the total height of clay layer divided by 2, because a water maximum distance will travel at 10 meter, not a 20 meter. Okay, because the water will go out from the top and bottom, from both sides. Okay, so you can take H is a 10 meter. So by putting all these value, we can get this result. So tau v we can calculate. So tau v we can get 0.1892. That is less than 0.28, means less than 60%. So we can use this formula. And by using this formula, we can calculate the degree of consolidation. So degree of consolidation we get 49.08%. So settlement we have 30 mm. So by using this degree of consolidation, we can calculate the small delta H. Delta capital H, because the total settlement we can calculate. So that we got 61.12 mm. is the total settlement occur for an infinitive time, that is 61.12 mm. Okay, so for 50 mm settlement we can calculate the degree of consolidation. So just we can write the 50 mm divided by 61.12 and we can get the degree of consolidation. So degree of consolidation is 81.8%, means settlement for 30 mm degree of consolidation was 49.08%. So for 50 mm settlement degree of consolidation is 81.8%. So for this degree of consolidation, so what time will occur? So we can calculate. So for in the previous slide I mentioned, for degree of consolidation greater than 60%, we will use different formula. So that formula is TB is equal to this. So by using this relation we can calculate the time factor, and that is 0.60835. Okay, and by using this relation, because now we have TB value, we have CB that is constant, and H that is 10 meter, that is also constant. So by using this relation we can calculate the time. So total time will take 6.43 year. So already we have spent 2 years. So what time will take from now? So that will be additional number of years will be, so 6.43 minus 2 years, that will be 4.43 years. Are you getting my point? Okay. First in this questions asking about the for what time will take for 50 mm settlement. So we have calculated the for 30 mm settlement what is the degree of consolidation, and then we have calculated the total settlement for the infinity time, what will the total settlement will occur, and from the total settlement we have calculated the degree of consolidation for 50 mm. So for 81.8% degree of consolidation, what time will occur? And that time will got 6.43 years. So what additional numbers of year will take? So 4.43 years. Next question is, in the laboratory test on a clay sample of thickness 25 mm, drained at a top only. So this is the example of, this is the case of single drainage system. 50% consolidation occur in 11 minutes. Assume TV50 means for 50% degree of consolidation TV value is 0.197, and for 20% degree of consolidation TV value is 0.405. So find the time required for the corresponding clay layer in the field of 3 mm thick and drain at the top and bottom to undergo 50% consolidation. Also find the time required to undergo 70% consolidation. So just first note down what are the data given. So in the laboratory, so what data are given? T50 0.197, time is taken 11 minutes, and H is the 25 mm and single drainage condition. So in the laboratory this condition was given. So now we can calculate. So we have TV, we can write that formula for time factor. So TV50 for 50% degree of consolidation. So we have T, that is 11 minutes. We have H, that is 25. So we can calculate the degree of coefficient consolidation that we got. That we get 11.136 mm square per minute. Right. And now we will discuss about the field. So in the field there is a condition of double drainage condition, and so double drainage condition we have to take the H, and that is the 3/2, because the field 3 meter thick, means the clay layer of thickness was 3 meter. So now is the case of double drainage. So water will take the maximum distance, that is the not H, means not 3 meter, it will take 1.5 meter, because water can be go from top and bottom. So we can take H is equal to 1.5 meter. So we have T50 0.197 and CV we got, because the degree of consolidation is constant for the field and for the laboratory. So again we can write this formula. So now we have TV value, we have CV value, we have H. So now we can calculate T, that is 27.55 T. And for 70% of consolidation we can write again this equation. Again we have time factor for some degree of 70% consolidation. So we have CV value, again we have age, so we can calculate the 56.52 days. So this in this questions there is a two things are given. So first, in the laboratory they have done some experiment, and that experiment was it takes 11 minutes for 50% degree of consolidation and thickness was 25 mm. So in the field they are asking about the, in the case of double drainage system, they are asking about what times will take, where the height of clay was 3 meter thick, and what time will take for degree for the 20% degree of consolidation. So we have calculated the both things. So one things we have to remember from these questions, the degree of consolidation, the coefficient of consolidation will be constant. It will not be vary. So by making the degree of consolidation is constant, we can calculate all these value. And these are the reference that I have taken. Okay, thank you.